Hey everybody, Trey here. The podcast you're about to listen to is an AI-generated discussion focused on a transcript from my Convective Chronicles YouTube channel. Artificial intelligence is something we are constantly experimenting with at Storm Chaser Coaching, and you might be surprised to know that what you're listening to right now is an AI clone of my voice. I hope you enjoy Convective Chronicles Reimagined.
It's just incredible, isn't it? Thinking about a single storm tearing across 4 states like that, producing violent tornadoes for hours on end. December 10th and 11th, 2021, the Quad-State Supercell.
Absolutely. It wasn't just the path length, it was the sheer endurance, the intensity. Really remarkable.
Makes you wonder, what allowed it to just keep going like that?
Exactly. What were the ingredients, the atmospheric conditions that let it not just form, but stay so ferocious for so long?
Yeah.
That's what we're going to dig into today.
Right. So think of this like we're investigators looking at this huge, destructive, but also kind of awe-inspiring event. We've got the technical breakdown, the meteorologist's analysis, their reports, basically. And we're going to pull out the key bits, the interesting stuff.
Yeah, translate it,
Mm-hmm.
Make sense of the why behind it, even if you're not deep into weather jargon.
Exactly. So we'll be asking things like, why did it last so incredibly long?
And why were the tornadoes it produced so strong?
And that big question, was it really one continuous monster tornado, or did it, cycle?
Yeah.
Multiple tornadoes.
That's a big part of the discussion, yeah.
Okay, so let's start at the beginning. The setup. Our source material talks about the bigger weather picture leading up to it. What was going on?
Well, the analysis points to what meteorologists call a zonal flow across the U.S. So imagine the jet stream, those high-up winds.
Just going straight across, west to east, mostly?
Pretty much, yeah. Not huge north-south dips.
Yeah.
But there was a trough, a dip, kind of digging down into the central U.S.
Okay.
Now, the interesting thing is, usually for the really strong outbreaks, you look for a trough that's angled sharply, negatively tilted. That often gives you stronger lift, stronger forcing.
Which might mean like a line of storms or clusters?
Often, yeah, or different storm types.
Mm-hmm.
But this trough, it wasn't like that. It was more neutral, maybe even slightly positively tilted. And here's the twist that set up. The weaker, broader push from the trough, and how the winds changed with height, the shear. It actually favored individual storms popping up, discrete supercells.
So, counterintuitively, a less dramatic-looking trough led to these more isolated, potentially more dangerous storms.
That's a really key point. Because the forcing wasn't overwhelming everything, these individual cells had the room, the environment, to get organized and really start rotating.
Gotcha. And were they expecting this mainly at night?
The main thinking was for nighttime activity, yeah. But they were also watching for maybe some earlier development during the day.
And wind shear, that twisting motion that needs wind near the ground too, right?
Oh, absolutely critical. There was this strong, broad, low-level jet stream, basically a river of fast wind closer to the surface, blowing from the south-southwest.
Okay.
And it really cranked up after dark. That provides the necessary spin, the shear, for storms to rotate. Wind at one level going one way, wind higher up going another. Yeah. Creates that twist.
And the air itself, was it ready to fuel storms?
Oh, yeah. You had this really wide area of warm, humid air, the warm sector sitting over the Ohio and Mississippi valleys. Southerly winds just pumping that moisture and warmth.
That sounds like a classic setup for trouble.
It's definitely a concerning profile when you're thinking about tornadic supercells, yes.
Now, what about the computer models? Did they start hinting at this becoming such a major event?
They did. In the days leading up, the models started showing this low-level cyclone, like a surface low-pressure system, slowing down a bit and maybe intensifying slightly.
Okay, subtle change.
Seems subtle, but the effect was significant. It led to the low-level winds becoming more backed, meaning more out of the south or southeast, and stronger.
And that specific wind profile is bad news.
It's particularly favorable for supercells that can produce these long-track tornadoes. It helps enhance that low-level rotation.
Wow. So a small tweak in the model forecast had big implications.
Exactly. And then you had the ensemble models. Those are runs with slightly different starting points to gauge uncertainty. They started consistently showing that warm sector getting even warmer and more moist as the event got closer. More heat, more humidity, that just ups the ante for tornado potential.
Okay, so the atmosphere is primed. Let's move to December 10th itself. How did things actually unfold?
Right, so that morning, you still had that broad trough, that dip in the jet stream in place. But crucially, there was also a stronger belt of winds, higher up, aloft. And this caused widespread gentle rising motion across that whole warm sector throughout the day. Synoptic scale lift, we call it.
And rising air is step one for storms, right? It needs to get going upwards.
Absolutely. And think of the atmosphere sometimes having a lid on it, an inversion or cap.
Yeah.
This broad lifting helps to weaken or erode that cap.
Like taking the lid off the pot.
Kind of, yeah. And the weather balloon data from Little Rock actually showed this happening. There was a pretty strong cap in the morning.
Okay.
But as the day went on, because of that lift, the cap got weaker, cooler, moister, and by evening, poof, it was essentially gone. The barrier to storms forming was removed.
So the instability was just building and building.
Precisely. Then there was another piece. A subtle little ripple, a disturbance higher up around the 700 millibar level, mid-atmosphere. A shortwave.
Okay.
That probably provided the specific little nudge, the trigger, that got this specific supercell going in central Arkansas.
The final push it needed.
Kind of. And because the push from that shortwave wasn't massive, and maybe there was still a tiny bit of cap left elsewhere, it didn't set off a whole bunch of storms all at once.
So that helped keep it isolated, discreet.
Exactly. Critical for it developing into such a well-organized supercell later.
And that low-level jet we mentioned, did it kick into high gear?
Oh, absolutely. It was strong to begin with, maybe 40, 50 knots, but through the evening, it just kept strengthening. Over 50, maybe 60 knots or more. That really fueled the low-level rotation potential. Vital for tornadoes.
And what about the bigger surface low out west? Where was that going?
That surface cyclone, which started out over like southeast Colorado, it was trucking steadily northeastward, and its movement was actually really important. It meant that the favorable environment, the warm, moist air, the strong wind shear, kept moving along with the storm, more or less. It sustained the conditions the storm needed.
Wow. So the storm kind of stayed in the sweet spot for a really long time.
In a way, yes. And the analysis also mentions these things called prefrontal troughs, little areas of lower pressure ahead of the main cold front. They were likely where the initial storms fired up. Storms in the warm sector along features like that often end up isolated because the lift is broad and weaker, and the orientation works out that way with the shear.
Okay, the ingredients are all mixing. When did things really start to, explode? When did the tornadoes actually start?
Well, early afternoon, the Storm Prediction Center, the SPC, they put out a mesoscale discussion, basically saying, okay, things are lining up. We're increasingly concerned about isolated supercells, potential for strong tornadoes later. A heads up.
Right, the warning bells are ringing.
Exactly. Then around 3 p.m. Central Time, you start seeing showers pop up near Arkadelphia, Arkansas, southwest of Little Rock.
Okay.
As they moved over Little Rock, radar started showing hints of rotation, that kind of bean shape, suggesting the storm's starting to organize, to spin.
That's when meteorologists really lean in.
You bet. Then, moving northeast of Little Rock, it clearly becomes a distinct supercell. By about 6 p.m., you see a low-level mesocyclone, the rotating heart of the storm, and even a BWE, a bounded weak echo region.
That radar donut hole thing?
Yeah, exactly. It suggests a really powerful updraft punching up, so strong that rain and hail can't even fall down through the middle of it. A serious sign.
Definitely.
Then it keeps intensifying as it heads towards Jonesboro. Mesocyclone gets tighter. Around 7 p.m. near Bay, Arkansas, the first tornado reports come in. Some reports even mention twin tornadoes.
Twin tornadoes, wow.
Yeah, pretty intense. Then towards Monette and Leachville, it got even stronger. Radar showed a classic hook echo, really well defined, and crucially, a debris signature radar detecting stuff being lofted by the tornado.
So confirmation it's on the ground and doing damage.
Yes. And that's when SPC issued another discussion, this time warning specifically about the potential for a violent tornado.
And tragically, that happened in Monette and other places.
Sadly, yes. The storm continued into the Missouri Boot Heel, Haiti, Caruthersville. Ground reports described a huge wedge tornado, and some observers even reported seeing horizontal vortices.
Horizontal vortices, what are those?
They're like sideways spinning tubes of air, sometimes seen near the ground with extremely violent tornadoes. It speaks to the incredible intensity of the rotation.
Just unimaginable power.
It really is. Now, there was this one radar reading around this time showing a velocity difference, the delta V, of like 283 miles per hour.
Yeah.
It's huge.
Yeah.
But the analysis suggests that was probably an overestimation, likely some radar artifacts, technical stuff. A more realistic but still incredibly potent rotational velocity was probably more in the 190, 200 mile range.
Still devastatingly strong. Okay, now the big one, this long path. Was it one continuous tornado the whole way, or did the storm cycle, producing multiple tornadoes?
Right, that's the core of the debate. The evidence gets really interesting as the storm crossed from Missouri into Tennessee. The radar showed that tight hook echo and the strong tornado vortex signature, the TVS. They weakened, maybe even disappeared for a bit.
Ah, suggesting it might have lifted.
That's the question. Now, supercells do cycle. They can regenerate. There's sort of classic ways this happens. Sometimes the rain wraps around, chokes off the old circulation, and a new one forms that's occlusion. Sometimes the rotation weakens and a new one spins up nearby. Cyclic mesocyclogenesis.
Okay, but this storm didn't quite fit those textbook cycles.
The radar data doesn't scream classic cycle. You didn't really see the tornado path take a sharp left turn, which often happens with occlusion. And you didn't see a super clear, distinct new circulation forming right next to the old one before the old one died off completely.
Yeah.
It wasn't textbook.
So if not a classic cycle, what's the leading theory?
The analysis leans towards the tornado likely lifting off the ground for a short time.
Okay, what's the evidence for that?
Well, the rotation signature on radar, the velocity, it broadened out. The debris signature seemed to vanish northeast of Sandburg, Tennessee. Importantly, that area is mostly wooded wildlife refuge, not many structures.
Right, so maybe less debris to pick up anyway, but also maybe no contact.
Exactly. And crucially, there weren't ground survey damage reports right in that specific segment.
A gap in the damage path.
Seems like it. Then, a bit further along, south of Moscow, Kentucky, before reaching Case, the radar shows a strong rotation signature spinning back up again, quite clearly.
So it re-intensified and likely produced a new tornado segment.
That appears to be the most likely scenario based on the data. Probably two distinct but very closely related long-track tornadoes produced by the same parent supercell.
Okay, so if the first one lifted briefly, what might have caused that weakening?
One strong possibility involves something called the rear flank downdraft, or RFD. That's the rush of cooler, drier air that descends on the backside of the storm. It's crucial for tornado formation, but
too much of it, or a surge, could disrupt things.
exactly. A strong surge of the RFD can actually undercut or disrupt the low-level rotation. The analysis uses an analogy, the EF3 bridge-creaked tornado from 2015, where an RFD surge clearly messed with the vortex, causing it to weaken.
So an internal hiccup in the storm's airflow might have caused that temporary break.
That seems to be the most plausible explanation. Yeah.
Okay, let's zoom back out to the supercell itself. We know it was incredibly long-lived. What were the key factors that allowed it to just keep going?
Several things came together. First, as we mentioned, it was mostly alone. Being discrete, isolated, meant it wasn't fighting other storms for fuel or getting disrupted.
It had clear sailing.
Pretty much.
Yeah.
Second, that environment stayed remarkably consistent. Remember that surface low moving northeast?
Yeah.
It kept dragging that warm, moist air and the favorable wind shear along the storm's path. It provided a steady-state, supportive environment for hours.
The conditions didn't really change much around the storm.
Not significantly, no. Third, there was persistent low-level warm advection. Basically, warm, moist air kept flowing into the storm at low levels, even well after sunset.
Continuously feeding the beast.
Right. The analysis even points out that temperatures and dew points ahead of the storm were actually increasing slightly late at night, which is unusual. It shows just how strong that inflow of fuel was.
Wow, a nonstop fuel pump.
Kind of, yeah. And finally, looking at weather balloon data or profiler data ahead of the storm showed the wind structure, the vertical wind profile, remained remarkably consistent over like a 40-minute period. Just a sustained, highly favorable setup for tornadoes.
It all just lined up perfectly and stayed lined up. Incredible. Now, the analysis compares this to a few other historic events, right? What can we learn from those?
Yeah, they looked at the Great Tri-State Tornado, March 1925. Another incredibly long track in a similar area.
The big one.
Right. Some similarities in the upper level pattern. A northeast moving surface low again. But a key difference. The tri-state tornado tracked right along a warm front, a boundary, for a lot of its path. The quad-state storm was mostly out in the open warm sector.
So different mechanisms were likely involved in keeping the tri-state one going for so long?
Seems like it. They also mentioned the March 12, 2006 six-state supercell, another very long-lived supercell, again with the moving low and broad trough.
Okay.
But that one produced multiple tornadoes along its path, not one continuous super long one like the quad-state segments. So it shows that a long-lived supercell doesn't always equal a single record-breaking tornado track.
Right. The storm can persist, but the tornadoes it produces might still cycle or be shorter.
Exactly. And finally, a brief mention of the April 27, 2011 super outbreak. Immense outbreak. The individual tornadoes maybe weren't as long as the quad-state segments, but the supercells that produced them were incredibly long-lived.
And similar ingredients there, too.
Yeah, again, that pattern of a broad, warm sector, a moving surface low helping maintain it, and an upper trough that wasn't sharply tilted, allowing for those discrete, long-lasting storm modes.
So that combination, the moving low, the big warm sector, the right kind of trough, seems to be a recurring theme for these marathon supercells.
It definitely appears to be a key combination for allowing these storms to persist and maintain severe potential for such extended periods.
Okay, so let's try to sum this up. The Quad-State Supercell's epic journey was really down to being isolated, number one.
Yep, crucial.
And number two, sitting in this incredibly persistent, favorable environment that just moved along with it, thanks to that surface low and continuous warm air inflow.
Exactly. A remarkably steady state situation.
And the tornado itself. Most likely two very long segments with a brief lift near the Tennessee-Kentucky border, possibly due to an RFD surge.
That's the interpretation that best fits the available evidence, yes. It was just an extraordinary historic event, really highlights how specific, consistent atmospheric conditions can lead to such extreme outcomes.
It really does. It makes you think, about how these huge weather systems connect. Like, how many other seemingly isolated extreme events are maybe subtly orchestrated by these larger, slower patterns? Or maybe, thinking forward, how can really understanding these long-lived supercells help us get better at forecasting better warnings?
Those are definitely the big questions.
Yeah.
It underlines why studying these extreme events in such detail is so incredibly important.
Absolutely. Well, that wraps up our deep dive into the Quad-State Tornadic Supercell, a truly fascinating, if destructive, meteorological event. Thanks for exploring it with us.
Thanks for tuning in to Convective Conversations. If you found this episode helpful, make sure to subscribe so you never miss an episode. Want to take your skills to the next level? Join us inside the Chaser Academy. That's our in-depth training program for storm chasers who want to chase smarter and safer. Just click the link in the description to subscribe. And if you're looking for community, we've got a free space where hundreds of chasers and weather enthusiasts are sharing forecasts, asking questions, and learning together. You'll find that link in the description too. Until next time, stay safe and keep chasing.